So our next talk is by Yury Balega, something like that. He is from southern Russia, and he is the director of the Special Astrophysical Observatory.
Thank you very much. So first of all, I would like to express my best feelings to be here, and many thanks for invitation to be here, because this is my second visit in the United States in my life. The first one was 21 years ago, exactly, in the Callaway Gardens in Georgia, Atlanta. It was a fantastic meeting. So it's a good impression. Sorry for my bad English, because in Europe we speak, not bad American, because in Europe we speak real pidgin English, and we understand each other very well, but not Americans. So, and second, I want to, just before giving this short talk, I want to say that there was a General Assembly IAU in Prague in 2006, and I have been giving a talk about speckle and adaptive optics, and Virginia Trimble from California, she was presenting, and I was complaining that we do not have enough time on large telescopes for doing speckle, and she said that it's correct for these allocation committees, because speckle does not give enough and important scientific results. So it's good that the allocation committees do not give you observing time. So therefore, from that time, I decided to change myself and started slightly new way of research. So I will tell you a short story about Orion trapezium and primary star in this interesting star-forming region, which is Theta 1 Orion C. Why about this star? Because this is a good example how speckle coupled with the spectroscopy, photometry, and other sciences, radio interferometry, gives a new astrophysical data. And maybe this is not the most important result, but for me it's important because I use many different fields of research. So, Orion Nebula is the nearest star-forming region. It contains few hundreds very bright and massive hot stars. This distance is very well known today. It's 412 parsecs. We know this from radio interferometry. So the distance to each of these stars is very well established today. And we see this bright trapezium, Orion, in front of the nebula, which is slightly behind. So the four stars, the four principal stars in trapezium, we observed them using speckle interferometry in the infrared and the visible, and we are surprised that all of them were resolved except D. D is on the left side, this one. So all of them were found to be binary or multiple systems. These are infrared images obtained in 1997. And of course, we tried immediately to follow their orbital motion. And for example, these components on Orion A and Orion B, very complicated structure. There is a jet from B1 in this direction, and inside of the jet, because of some reasons, there is a binary which we are following its orbital motion now. Of course, these objects have been observed also using adaptive optics, so there are many data about these stars. But I will speak about this star, which is the principal source of ionizing radiation in the nebula. The total mass of the system is about 45 solar masses. We don't know exactly all the masses up to now. So we resolved in here, 1997, using infrared speckle and a 6-meter telescope, and then followed for almost 15 years. This is an orbit which we built recently, including the data obtained with VLTI interferometer and IOTA interferometer, which does not exist anymore. So altogether gives us this more or less nice orbit. And from this orbit, we can calculate these orbital parameters of the star. So what are the principal problems which we want to solve with the Theta 1 Orion C? First of all, how these very massive stars form. And of course, Theta 1 Orion C is the nearest very massive, very young star. The age of the star can be about something between 100,000 years to 300,000 years. It's a very young star. It was born much later than the Homo sapiens appeared. I don't know. It's a young star. The second question is what is its chemical composition? Is there any different with the present day cosmic matter, which we know in the solar vicinity? Yeah, and the magnetic field was found for this star recently, about 5 or 7 years ago. So the magnetic field is probably the reason for very slow rotation of the star. We'll talk about this, and also very interesting problem, the well-known Backlund-Neugebauer object, which is running away from this, seems to be running away from Trapezium Orion. Was it ejected from this system? So many questions which are very interesting to study. And first of all, we use the parameters which were calculated from our interferometric orbit. So these are the temperatures, luminosities, masses for both components. But the spread of the parameters is very large, so it's very difficult to make models of the star. So model atmospheres were calculated using these parameters, and we used the turbulent velocities in the star, and of course we had to collect a lot of spectra of the star with high spectral resolution. High, I mean about between 40 to 50,000 spectral resolution R. And signal-to-noise ratio to get to very weak lines of the secondary components have to be about 1,000 or up to 2,000. So this is the task for large telescopes. And it's not interesting. I will not lose the time. So this is a good example of comparison of the theoretical profiles, which is black, and observed profiles of the lines for all 3 lines. So corresponding to different velocities of the star. So it gives you the impression that the modeling is good enough. And the problem, what is the rotation of velocity of both components, the primary star and the secondary? And in the literature you can find the spread of where V sinus I between 20 and 150, so it's very big spread of data, so it's not possible to find the velocity, rotation velocity of the star from the literature, so we had to measure the equivalent width of our lines, and we found that it's about 35. The rotation period of the primary is known very well now, it's 15 days, so it's in good correlation with our width of the lines. And this again profiles, so it's not interesting. And what about the secondary? The secondary is smaller. It has the mass about between 8 and 10 stellar masses, while the primary is 35. So the secondary is smaller and it's cooler than the primary, and therefore its lines are very weak. If you look at the spectrum, you can see that the depth of lines is about 1 or 2%. So it's very difficult to study. But the lines are very wide. So from this we could estimate the rotation velocities for the secondary. And it's rotating fast as it has to be for such stars. So rotation velocities, it's not here. Yeah, it's about 150 kilometers per second. So the primary is rotating slowly, which is big, and all 6 spectral type star, and the secondary is rotating very fast. And then the best model fit, and we try to find the lines of the secondary in the spectrum. So because it's cooler, so there are some elements like silicium-3 which can be observed only in the spectrum of the secondary. From these very weak silicium-3 lines, we could measure the rotation velocities and radial velocities of the secondary, and this belongs to the primary. So you see there always a difference. This is our attempt to find the velocities for both components. The weak secondary, red dots, and the primary is here. And finally, using different tricks, we have these radial velocities for both components. So this is spectral binary 2. And it has to be improved, but in principle, we now have the spectra of both components. We have radial velocities, we have orbits, so it's 3-dimensional orbit of the star exists, and now we can determine the masses with much higher precision. Then again, to come back to spectroscopy, to improve our modeling of the star, and so on. So it's a long process, but in the end, we hope to get the from the spectra and from interferometry, we hope to get the masses with an accuracy of about 5%. So that's our goal. The next question is about the, as I mentioned already, about this Beckley-Neugebauer object, which is here. This is Orion trapezium here. And if you study the velocities, proper motions of these stars in trapezium, you will see that the brightest star, the trapezium Orion C, is moving with a comparatively light speed. The velocity is about 4 kilometers per second, while for all other stars the dispersion is 10 times smaller, lower. So it's very fast moving in this direction. And from another side, this Beckley-Neugebauer object is running away at the speed of 30 kilometers per second. And direction, you see, more or less coincides with the position to the trapezium Orion. So, of course, the idea appeared that this object, which is cool object, and it is a very active star-forming region around here, is running away because of some collisions in the system of trapezium Orion C. So it's very strange. And there are many arguments supporting this idea. For example, the missing mass, stellar mass, is required for how to pronounce virial? Virial, that's the same. In French, it's virial or in Latin. So virial equilibrium in the innermost part of the nebula here. Also, the mass of the secondary in Orion, Theta 1 Orion C, is high enough to give the idea that the Beckley-Neugebauer was ejected as a third star from the system of this binary. So it's ejected in this direction. And also kinetic energy can be calculated, very simple. And eccentricity of this system is also good fits to the idea of that BN was ejected. But there are also some other possibilities that, for example, this so-called source I also lies in the same position, and Beckley-Neugebauer and BN and I could be the result of some recent event somewhere here. So it's not studied, not confirmed up to now. So in general, the main problem of the proper motions for these stars is that they are moving too fast, and virial so it means that in comparison with all other stars in Orion Nebula, they are moving too fast. So probably there were very massive bodies. There are even ideas that there were black holes here, which concentrated all the gas and the mass from the inner part of the nebula, and we don't see them now. They probably were ejected somehow. So it's a very complicated study, and we have to analyze this possibility. We study the motion of the A binary and B to 3 motion. This is long time motion. The period has to be about 150 years. And for this astrometric speckle and astrometric studies, we hope to estimate the possibility that there are some massive bodies inside of the, not visible, massive bodies inside of in the center of Orion Nebula. And last, what I wanted to mention that about the magnetic field. So very briefly, this is a Theta 1 Orion C and rotation axis, and it has magnetic field, dipole magnetic field, probably inclined. So it's rotation, and there is a magnetic equator. So the material which is the star is losing is concentrated along the magnetic equator here, and this is the effect which breaks the rotation of the star, because the more material the star loses, the stronger is breaking. So there are very simple calculations, and Well, it's not interesting. Hypothesis is, you see it's written here, that we assume that the two stars, A and B components, when they were formed, they were rotating with more or less the same velocity. Now the primary is rotating very slow rotation, so probably it lost this rotation velocity because of the mass loss and because of the existence of magnetic field. And this can be estimated from more or less simple formula. And this is the last slide. So we can estimate the spin down time for the primary components of the star. And unfortunately, the spin down time is much more than the age of the star. So it's about 10 mega years. I'm finishing. So it means that the magnetic break-in, or it doesn't work, or we do not know the parameters of mass loss for the star, etc. Because this is very big problem. So I would also like to mention that there are another examples of O stars which are rotating very slowly. These two, for example, here. And HD 108 is rotating with a period of 15 years. This is spin of the star, 15 years. So it's very slow rotators. And all of them have magnetic fields of the order of 1 kilogauss. Kilogauss, yeah. So maybe this is very typical for O stars, very massive stars, that if they have a magnetic field, if this is a magnetic field, I do not speak about the origin of this field, but if this is dipole, simple geometry magnetic field, so this can cause, in cooperation with the mass loss, intensive mass loss, they can cause the breaking of the star. So that's all I want to say. Thank you very much for your attention. This is a good example of the star, which is very complicated. It comes to us from speckles, and we have to continue with speckle observations because the orbit has to be improved, motions of another components of Orion trapezium has to be studied, and this will continue for a long time. Thank you for your attention. Questions? Have you? Two questions. Yeah, please, allow it.
So I'm just wondering, so this is an argument for speckle, which I think is great, but yeah, what about for also classical astrometry, right? I mean, how well is the classical astrometry of this field known, and is that something that could be improved?
Yeah. We need some new ideas how to improve the astrometry of the components of Theta 1 Orion in Orion trapezium. Yeah. So there are 4 stars, something like that. And if we can measure distances between these with precision accuracy, which is better than today, factor of 10, so probably we can, and taking into account the wobbling caused by the binarity or multi-structure of these components, so probably we can see the oscillations of these distances caused by the presence of some unknown bodies, because we need them, these bodies. They're like a dark matter in the universe, but there is a dark matter of factor of 10, more than what we see in the nebula. So we must have about 2,000 massive stars in Orion Nebula here. But what we see is only less than 200s. So the factor of 10 is we need the lack of mass. And classical astrometry probably can help us. Of course, this Orion trapezium is observed for centuries. But the accuracy, the precision of this measurement is low for this goal.